Hi everyone, can you all hear me? Okay, great. So we can start the class. Yeah, so today we will be continuing from where we had left yesterday. So basically we will march on to our journey of trees. So yesterday we had solved some really simple question on trees. By the way, did you guys get some time to practice those questions? How many of you coded those questions? You can type in yes in the chat box if you did. Okay, cool. It's important to code those problems because those are quite interview-centric problems. So if you code them, you will have enough confidence to crack them if you face them in your interviews as well. Yeah. Okay. So today we are going to solve some more interesting problems on binary trees. So yesterday I told you about a term called as height. So now what we'll do is we'll try to find height of a binary tree. Okay, so for that I need to define what is the meaning of height. So the meaning of height is it is the longest root to leaf path. So let me write it here. It is the longest root to leaf path. Okay, so let's take a quick example. Let's say we have 5, 2, 1, 9, and you have 1, 3, and 7. Yeah, so this is your binary tree. Can you tell me the height of this binary tree? Okay, so it looks like some of you are saying 4 and some of you are also saying 3. So let me tell you one thing. What is the longest route to leaf path over here? The longest route to leaf path is this one. Correct? Now, some of you are calculating the number of nodes along this path. So number of nodes is 1, 2, 3, and 4. And some of you are calculating the number of edges along this path. So number of edges is 1, 2, and 3. So of course, if number of nodes is n along any path, the number of edges will be n minus 1. So there are different definitions of height. Some people say that height is equal to the number of edges, and some people say height is equal to the number of nodes along that path. So I'll stick to nodes. We will stick to nodes. So for us, height is equal to the number of nodes along the longest route to leaf path. Cool? Okay. Now, given the root of a binary tree, so let's say this is the root and you know about it, you have to write a program that computes the height of the tree. Okay, so that is what we want to do. How many of you can think of a solution to this problem? Any ideas like how can we move on? Oh, one of you is saying using recursion. Quite interesting, you know, in almost even almost is not the right word. In all the question of trees, you will be using recursion. So what is the key idea? Okay, Tanush has written some equation, some recurrence equation. Okay, so what was the most important thing that I told you yesterday? Given a binary tree, if you have to solve a problem on top of it, you have to decompose it into 3 parts. Do you remember that? What were those 3 parts that you had to decompose it into? Overall root, left subtree, and right subtree, correct? So any tree that you have to think of it as there is a root which has some left subtree and which has some right subtree. This is your root. Okay. Now tell me one thing. What you want to do is you want to compute the height of this big tree, right? Tell me one thing. If you know the height of this subtree and also the height of this subtree, will it be easy for you to compute the height of this big tree? Yes or no? What do you feel? Right? Yeah, that is exactly we will do. So let's just take a look. I'll draw this tree here again. So you have 5, 2, 1, 3, 7, and here you have 1, and here you have 9. I can say one thing for sure, that the height of the tree will be something that definitely passes through the root. It definitely passes through the root because you're clearly saying it is a root to leaf path. So the contribution of root will definitely be there. You're counting the number of nodes along the maximum path. So the contribution of root as a node will definitely be there. Now, on the top of that, either the height of this will be taken into account or the height of this will be taken into account. So if you look at this as a separate entity, can you tell me what is the height of this tree? This left subtree, how much height does it have? It has a height of 3 units. And what is the height of this? It has a height of 2 units, correct? Now I would say that, hey, instead of taking a path in this right subtree, I would want to take a path in left subtree. Why? Because the height of this is more than the height of that, correct? So I would say that, hey, along this thing, if I further include that thing, then my job will be done. So this is the contribution of your root, and this thing is nothing but the height of your left subtree. So I can say that height of the entire tree which is rooted at this root, if I write it in this manner, then this thing is equals to 1 plus, why 1 plus? That is for the contribution of the root. 1 plus maximum of the height of left, comma, height of right, correct? So height of root left, comma, height of root right. So it means that if I know the height of my left subtree and the height of my right subtree, then I can just figure out the max of those, add 1 to it, and that will be the height of the overall tree. Does it make sense? How many of you understood the idea right over here? Simple enough, isn't it? Okay. Now, yesterday I told you one more thing. Any such recurrence relation or equation that you write will have some base cases, will have some edge cases. So can you tell me for what kind of root would you not want to execute this equation or this piece of code? What should be the value of root for which you won't run it? Yeah, when your root is null. When your root is null, then if you do null arrow something, you will end up getting null pointer error. So there has to be a separate case when the root is null. So tell me, if the root is null, then what kind of tree is it? It is an empty tree. And what will be the height of empty tree? 0. Some of you are saying 1, 0. In an empty tree, there are no nodes. So the longest root to leaf path will be 0. So I can say that if my root would be null, I would simply return 0. And for the normal cases, I'll return this. This is how my code would work. Can you all write a function that computes the height now? Can you write the code? Yes or no? Easy. It will be extremely easy. So let us just quickly take a look. So let's say I need to get height. This is my height function. It takes the root of some tree or subtree and it returns the height. The first thing that I'll make it do is, if my root is null, that means the subtree that we are talking about is empty. So the height of that will be 0. Otherwise, what I'll do is I'll first compute the height of the left subtree, then I'll compute height of the right subtree. How do you compute the height of left subtree? By just making this recursive call on root left. Okay, so I'll call this function height for root left, and it will supply me an integer. I'll call that integer as left height. Similarly, I'll call this height for the right subtree. and it'll give me right height. And now all that I have to do is I have to return 1 plus max of LH comma RH. That's it, job done. Is it clear? How many of you understood the code properly? Okay, very good. So what is the time complexity of this code? If there are n nodes in the tree, how much time does it take? Order n is correct. So those of you who are having difficulty understanding the time complexity, let me tell you, see, in reality, what you're doing, no matter which node of the tree you are at, let's say this is a huge tree. No matter which node you are at, if you are at this node, all that you are doing is you are making this call, you are making that call, and you are getting two integers from here. Those integers are LH and RH. And with those integers, you are finding their maximum and adding 1 to it. And this is almost constant time operation only. So I can say at each node, you are finding max of 2 integers that is being supplied to you and adding 1 to it. So if there are n nodes, because you are doing constant work at each node, your overall complexity will be order of n. Does that make sense to everyone, that how the time complexity here is order of n? I would also encourage you guys to go ahead and make a recursive tree diagram of this the way I had made it yesterday, and see for yourself that how the values are being returned and how the height is actually being computed. Yeah. Can you draw that? How many of you can draw that recursion tree diagram corresponding to this code? Correct. Okay. What I'll do is, just to help you guys understand it better, I'll draw the recursion tree diagram. You know, by the way, you should yourself be drawing, according to me, you should yourself be drawing recursion tree diagram of every code that you see, because the more you draw, the more comfortable and more expert you become, right? So now you have this code, you know what are the steps to draw. So I'm drawing it once, and from now on, I think you all should imbibe this habit of drawing it. Okay. So when I look at this function, this is a height function. I'll first call it for the overall root, which is 5. So this has been called. Now, all that you have to do is you have to look at it and you have to figure out how the code control flows. So this thing, it is not null. So this condition will be skipped. You will come here. Coming here means you will invoke the call on the left child of 5. So you will call height function for 2. And here you will call height function for 1. Okay. Now we know how recursion works. You come from here to here. So now you are at this particular node. This particular node again is not null. So you will make a call to the left and right child of 2. The left child is 1. So you will call height of 1. And the right child is 3. So you will call height of 3. So now you will come from here to here. Now again, you are at this node, which is not null. So you will make a call to the left and right child of 1. What is the left child of 1? The left child of 1 is null. What is the right child? That is also null. So you will call height for null and height for null. So control came from here to here, here to here, here to here. What will happen at this point of time? Just look at the code and tell me. It will return 0. Just look at the code. It very clearly says that if the root is null, return 0. What is the meaning of this line? The meaning of this line is that if you want to compute height of a tree whose root is null, then its height is 0. That's all that it's saying. And here, in reality, you are trying to find the height of this tree, which is 0. That is the reason you should be returning 0 from here. Okay. Now this call would be made. Again, from here, you will return 0. Now, when height of 1 was called, You made a call to your left child, got 0, made a call to your right child, got 0, and now what will you return? This function will return 1 plus max of 0, 0. 1 plus max of 0, 0 is 1. So it will end up returning 1, and it is correct to return 1 because height of 1 means height of just this much tree, and height of just this much tree is 1 unit. Do you see how values are being returned from the bottommost nodes and how they are being consolidated and how they are being sent upwards? Is it making sense to everyone? Yes or no? Yeah. You know, same thing you can keep doing on and on. So height of 2 will now invoke height of 3. So what is this 3? This 3 is not null. So you will call left child and right child of 3. The left child of 3 is 7. So you will call height for 7. And then you will call height for null. Now you are at 7. So again at 7, you will call height for the left child of 7 and height for the right child of 7. So the left child of 7 is null. The right child of 7 is also null. And from null, we return 0. And now what will happen here? Here, you will return 1 plus max of 0, 0. Your left height and right height. So you will return 1. And it makes sense to return 1 because when you look at the tree rooted at 7, its height is 1 unit, correct? Similarly, this is again null. You will return 0 from here. And from here, you will return. Can you tell me what will height of 3 return to its parent? It will return 2. So it will return 1 plus max of left height comma right height. Left height is 1, right height is 0. Max of 1 comma 0 is 1. If you add 1 to it, that is 2. And it is again correct to return 2 because the height of this much part is 2 units. Now again, what will you return from here? 1 plus max of 1 comma 2, which is 3. So you return 3 from here, which again is correct because when you look at the tree rooted at 2, its height is 3 units. Similarly, can you draw this part like height of 1 calls height of 9, and then can you draw that part on your own? Yes or no? Okay, cool. So what will this return? Any ideas on what will height of 1 return? It will return the height of this part, which is 2. And now what will this return? It will return 1 plus max of 3 comma 2, which is 4. That's how you will get an answer of 4. Is it now making sense to everyone how the code works? Correct? Yeah. So again, just to let you know, termination condition is the first part of your code, which you will be writing in your all the problems of trees. And then you call it as calls to LST and RST, or you call it as recurrence relation, which shows that how height of root is dependent upon height of root left and height of root right. If you learn how to craft such kind of equations with appropriate termination conditions, almost all the job is done. Okay, very good. Let's move on. Okay, so now we are going to solve a problem which has been very frequently asked in interviews. Okay, so we will be given a binary tree. Okay, before we move ahead, let me ask you a very quick MCQ kind of question. So we have a binary tree, okay? We have a binary tree with n nodes. What can be the maximum value of its height? Yeah, maximum value of the height will be n. And when will that happen? That will happen if all the n nodes are lying along the same line, which is the case of a skewed tree. Okay, my next question is, what will be the minimum value of height of a binary tree? Zero. If there are n nodes, okay? Now think and tell me, what will be the minimum value of height? Let's take example only. Let's say n is equals to 7. If n is equals to 7, you have got 1, 2, 3, 4, 5, 6, 7. 7 nodes along the same line. Here the height is 7. And if there are 7 nodes, just you take out your pen and paper and tell me what will be the minimum height. Minimum height will happen when you have got a perfect tree. This case, here the height is 3. Does it make sense? Yes or no? Correct? Yeah. And I had told you that when you have got a perfect tree like that, comprising of n nodes, then the height of this is log of n base 2. Correct? So I can say that if there are n nodes, then the minimum value of height will be log n base 2, and the maximum value of height will be order n. And it all depends upon what is the structure of the tree. If it is skewed, it will be a tree having huge height. And if it is perfectly balanced, then it will be log of n base 2. It's an important point. Is it making sense to all? Yes or no? Okay, great. Let's look at that question now. We have been given a binary tree, and what we want to do is we want to print all the root to leaf paths. Print all the root to leaf paths. So let's say your binary tree is like that. How many root to leaf paths are there in this tree? There are 3 root to leaf paths. Can I say that number of root to leaf paths will simply be equal to number of leaves? Isn't it? Like, see, there is only one root, but there are multiple leaves. So this is one path. So this is 3, 4, 5. And this is another path. This is 3, 4, 7. And that is the final path, which is 3, 2, 9. So similarly, there can be multiple root to leaf paths. I want you to write a code which prints this data, which you can see right now on the board. Is the question making sense to everyone? Yes or no? Okay, if it does, can we come up with some solution? Okay, you guys just tell me one thing. All of you have learned recursion in your 2nd or 3rd class, right? So can you tell me some problems that you solved in recursion? Tower of Hanoi, very good. Any other problem? Factorial, okay, good. Keypad of a number, count paths, pyramid of glass, number of paths, many problems like that, right? You know, if you stick to the concept used in any one problem, you can use that concept and solve this question literally very, very easily. It will not be a tough task for you for sure. Okay, so let's talk about it. This is a problem which you can easily solve using recursion again. So let's look at the board now, everyone. This is quite important. Let's say there is a big tree, okay? There is a very big tree. I'm just drawing a small portion of it. So let's say it has an edge coming from some node, and here you have got a 4, and here you have got a left subtree of 4, and here you have got a right subtree of 4. It's a big tree, by the way, okay? And there is root somewhere. Let's say root is present over here, something like that. Now, answer me one thing. there will be some root to leaf paths which are present in this left subtree. When I say present in left subtree, I mean to say that there will be some root to leaf paths whose leaves are present in this left subtree. And there will be some root to leaf paths whose leaves are present in this right subtree. Can I say all such paths that cross this 4 and land here, 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 or here will have 4 in them? Just think, any path that goes like that, that, or that will definitely have 4 in them. Is it making sense to all? Yes or no? Right? Okay. So it means that if I am there at a node, let's say I am doing a recursion on this tree. I'm visiting the nodes one after the other. Okay. And I'm doing that using recursion. So if let's say I am at 4, then it means that all the paths that cross 4 will have 4 in them. So how many paths are there which cross 4? This is one path, this is another path, and both the paths have 4 in them. So what I'll do is whenever I am at a node, I'll put that node in an array or in a list or in a vector, whatsoever you want. Okay. And after putting that in a particular list or vector, I'll make a call to the left subtree and I'll make a call to the right subtree. And while making those calls, I'll pass that vector or I'll pass that list. Okay. This is the idea that I'm trying to convey. So let's just take a quick example. I'll draw. So look at this particular tree. What I'm going to do is I'm going to make a call at this particular node. When I make a call at this particular node, let me draw it. Let's say this node is 3, and I'll pass over here an empty list, an empty array, whatsoever you say. Okay. And now, because I am at this node 3, I know for sure that all the paths that passes through 3 will be having 3 in them. So the first thing I'll do is I'll push this 3 in this vector or array, whatsoever you say, and then I'll make a call to the left child and the right child. So when you push this 3 inside this, you will have 3 over here, and then you will make a call to the left child, which is 4. Okay. And then you will also make a call to the right child. So 3 has been pushed and the right child is this 2. Now I'll keep doing this thing in a repeat mode. So when I am at this node 4, I know that all the paths that cross this 4 will have 4 in them. So I'll push this 4 in that vector, and that way I'll have 3, 4 with me, and I'll make a call to the left and right child of 4. So you make a call to the left child, you make a call to 5, and now you have 3, 4 with you. Similarly, you make a call to the right child, you go to this 7, and you have 3, 4 with you. You know, this is how I'll keep going down. Now again, when I am at 5, I'll push this 5 inside it. Okay. And after pushing 5 inside it, I'll make a call to the left and right. So I'll push this 5, I'll have 3, 4, 5 here, and the left child over here is null, where maybe I can terminate. So this is the idea that we'll be trying to use. We'll have a vector with us. In that vector, we will push the current node, and then we will pass that vector to the next recursive call, which is to the left subtree and also to the right subtree. This is what we'll keep doing. Is it making sense? How many of you are getting the idea here? Yeah. Okay. However, there is an important thing that I wish to tell you. So if you are using a vector, have you guys learned a little bit about backtracking? What is the basic idea of backtracking? The basic idea of backtracking is that if you are doing something, you also have to undo that thing. Okay. So it means, let's see, when you are at this node, you are pushing this node inside this list. When you have pushed this node inside this list, you make a call to left, you make a call to right. That's totally okay. Now you are at 4, you push this 4 inside this list. And then you make a call to left, you have 3, 4 at this 5, and you make a call to right, you have 3, 4 at this particular thing. Now, when this particular recursive call is over, should you not remove this 4 from the list? Because when this call is over, you will come back over here. And when you come back over here, you will start considering these paths that go in this direction. Now, the paths going in this direction will not have 4 in them. So it's your responsibility to remove 4. So whenever you are at a node, the first thing you do is you push that node. And after pushing that node, you visit the left subtree, you visit the right subtree. So far, everything is okay. But once you have visited all the paths that emanate from that node, now it's responsibility to pop that node, because if you do not pop that node, that will be reflected in the other paths as well. Is it making sense? Just type in yes or no. Yeah. So this is exactly what backtracking is. You do something. So pushing is like doing something, and then you make your recursive calls, and then you undo that thing. Undoing means, in this instance, you just pop that particular node. As simple as that. So this is what we'll be doing. Now, if you take a look at the code, it goes something like this. So let's say I have got a method called as print paths. It is void because it does not return anything. It simply prints all the paths out there. Okay. So here you are passing the root of the tree and you are passing a vector. So let's call that vector as temp. Mind it, you are passing it by reference. Okay. Because whatever change you have done to this vector, if you have pushed this 3, you want that push to be reflected here as well as there. That is the reason you can't pass it by value. You have to pass it by reference. Okay. Does that make sense? Yes or no? So let's say I want to write this code. Let's first talk about this idea. This is what you do whenever you are at any particular node. So whenever I am at a particular node, the first thing that I do is I push that node in my vector root data. This is what you do. And after this, what is the next step? The next step is to make a recursive call in the left subtree. Making a recursive call in the left subtree means calling print paths for root left and passing your temporary vector. And then you will make a call to the right subtree also, which is rooted at root right, and you will pass your temporary vector. Do you see that I have pushed this thing and then I have made a call to my left and right? Why? Because I know for sure that all the paths in my left subtree and in the right subtree will contain this node. That is the reason after pushing it, I have made those 2 calls. But when these 2 calls are over, that means I have visited the left as well as right subtree emanating from this node. Now this node is no more useful for me because now in the other paths, this will not be reflected. So now it is my responsibility to do temp.pop back. So this logic is your backtracking logic. This is what I had written over here. Is it making sense to everyone? Yes or no? Yeah. One of you is saying, shouldn't we pass star temp? That is the construct of C language, not the C++ language. If you have mentioned this ampersand over here, then by default, this temp will be, passed by reference, not by value. Okay. Cool. In this code, there is something which is missing. And what is that? Termination condition. Very good. So what will be my termination condition? Can somebody suggest that? Okay, one of you is saying I should terminate at leaf node. Okay, how about having a termination like that? I can say, okay, like look at this scenario. 5 left means you reached null. Keep looking. You reached null. And by the time you reach null, you have the data of this path in your vector. So you can maybe print it. So I can say that, hey, if my root is null, then I'll have a logic over here which will print the contents of this temp. And after that, we will return, we will exit. So can I have this simple termination condition with me? Yes or no? What do you feel? Okay. So this is quite interesting. A lot of people who even I have interviewed, I have seen they write such kind of code, and this code has a major flaw. You know what will this code print? See, if this is your input and this is your code, can you quickly dry run it and tell me what will be its output? So for that, you can just focus your attention over here. See, this is already the recursion tree diagram of this code already. So you were at this node, you pushed this 3 and you made a call to the left child, and then you made a call to the right child. Now again over here, you pushed this 4, and that way you made a call to the left child and then the right child, 5 and 7. Now again at this 5, you will push this 5 inside it, and you will make a call to the left child and also to the right child. Okay, also to the right child, 3, 4, 5. Now what will happen here is, this is the case where the passed node is null. So you will print 3, 4, 5. And this is also the case where passed node is null. So again, you will print 3, 4, 5. So what has happened is, you have printed this path 3, 4, 5, not just one time, you have printed it 2 times. Is that making sense? Yes or no? If we are terminating at null, what is happening over here? Do you get that? Correct? Others, yes, no? Yeah. So that's a big problem over here. And you know, this problem will only amplify. Think of it. By the time you are here at this node, when you are at this node, what will you do? You will push this 2 inside this vector, and you will have 3, 2, and you will make a call to the left child of 2. The left child of 2 is null, right? Now again here, because this is null, you will print 3, 2. Now tell me one thing, do you want to print 3, 2? Do you want to say that 3, 2 is a root to leaf path? The answer is no. Why is the problem happening? Because the way your code is written, the way your termination condition is written, you are trying to print root to null paths. You are not printing root to leaf paths, you are printing root to null paths. So if I attach the null, this is one null, this is another null, this is one null, this is another null, this is one null. So in reality, this code will print 3, 4, 5 at this null, 3, 4, 5 at this null, 3, 4, 7 at this null, 3, 4, 7 at this null, 3, 2 at this null, 3, 2, 9 at this null, 3, 2, 9 at that null. Do you understand it? Yes or no? Correct? So in questions like these, whenever you see that you have been asked to print all the root to leaf paths, or you have to do something at leaf, if the question is a function of leaf, then instead of terminating at this particular thing, it's better to terminate at leaf. So this is a really, really important point to understand. So how do I fix this code? How many of you can fix this code? How many of you can do that? You can, right? So what I'll do is I'll just make a few changes over here. So let us erase it for now. Okay. So what I'll do is, let's say I was at 5. At this 5, I pushed this 5 inside it. When I pushed 5 inside it, I got 3, 4, 5. But once I got 3, 4, 5, then I do not need to make further calls. Why? Because this 5 is a leaf. So over here, I'll have some condition. Okay, just look at that. So I'm going to write something in this part. I don't have space, so I'm writing it here. So I would say if root left is null and root right is also null. If that is the case, that means the current node is a leaf. And if the current node is leaf, then I'll print the contents of my temp, and then I'll return. That's it. And if that is not the case, then only I'll make a call to the left, I'll make a call to the right, and then I'll do a temp dot pop back. This is how it will happen. Okay, so you can put this thing in an else condition from here to here. Does it make sense? Yes or no? Yeah. So this thing will make sure that when you are there at a leaf node, when you are there at the leaf node, you are pushing that leaf node, but after making that push, you are checking whether your R is leaf or not. If your R is leaf, then you are printing the contents of your temp, and then you are just returning. Okay. In fact, this return would not be needed over here because you eventually have to pop back as well. You just print the contents of your temp. Otherwise, you are doing these two things. So if you are at a normal node, you push it and then you make a call to left and right. That is what you are doing over here. And then you are popping back. Yeah. Please explain. That is just a check for R, whether R is leaf or not. How do you check whether a node is a leaf or not? By checking whether its left child is null as well as right child is null. Correct? That is what. Okay, now some of you have a very good question that, hey, in that case, what to do if certain times the root is null? And that can very well happen. See, if you are at this node, you might make a call. In fact, you will make a call to your left as well as right. Correct? Now, when you make a call to your left, if that is null, then because of this check, you will get null pointer exception. So what to do? You will add one more check over here. If the root is null, just return. Don't do anything. So it means that if you have ever reached at null, at that point, you will have 3, 2 in your array. So at that stage, you don't have to do anything. You simply return. Correct? You know, similar sort of thing we had done yesterday also when we had written a program to calculate number of leaves. Do you remember that? We wrote a program to calculate number of leaves, and there as well we had 2 termination conditions. First termination condition was at the leaf itself, and the second termination condition was whenever our root got null. So we are doing exactly that over here. If we touch a path, if we ever stumble upon a null, we are not going to do anything. Otherwise, the first thing that we are going to do is we are going to push the node. Now, if the node is a leaf, we are going to print the contents of array. Otherwise, we are going to make a call to the left and right. And finally, we are going to pop whatsoever we had pushed in the array. Okay. Not able to understand what exactly the backtracking part is doing while calling left and right side of a node. We are already pushing and passing. So please explain again why backtracking is needed. Okay. Cool. Have you guys learned about backtracking in your second and third classes? Yes or no? Can somebody answer that? Who's that? Okay. Okay, cool. It's a very tiny concept. I can quickly talk about that. So let us understand that. Okay. So let's understand it. When you look at this code, you are carrying a vector with yourself, which is initially empty. Okay. And you start your journey from the root. So you are there at the root and you have an empty vector. Just keep looking very clearly. It's a very, very small thing, not a very Herculean thing to understand. You just have to put your attention. So you are there at this node. What you do is you push this node inside that. When you push this node inside that, you have 3 with you and you make a call over here. Control comes from here to here now. You realize that? Okay. So I'm not going to write something over here. Now at this 4 again, you will push this 4 inside this vector. When you push this 4 inside this vector, you will have 3, 4 with you. And you will make a call to your left child, which is you will come at 5. This call has been made. And you will also make a call to your right. When you make a call to your right, you come at this 7. And what do you have? You have 3, 4 with you because you had pushed this 4. Now when you are at 5, again, you will push this 5. You will push this 5 inside this. When you push this 5 inside this, what happens? This thing gets converted to 3, 4, 5, right? And after it gets converted to 3, 4, 5, you will print its contents. Printing its contents means you will print 3, 4, 5. Now just tell me one thing. Do you want to continue carrying this 5 with you? Let me erase this from here. Do you want to continue carrying this 5 with you? The answer is no, because 5 should only be reflected in this subtree. When recursion has terminated from here and comes back to here and you take this path, you won't want to take this 5 along with you. Is that making sense to those of you who are asking question around why backtracking? Yes or no? Yeah. So what is your responsibility? Your responsibility is that whatever you have pushed, that you should pop. And when you pop that, what will happen? When you pop this 5, then you will come back from here to here. Correct? And now this recursion terminates. You come over here, you make a call towards your right child. When you make a call towards your right child, 3, 4 gets passed over here. Why 3, 4? Because 5, which you had pushed over here, you made sure to pop that as well. And now you come over here at this node, which is 7. Now again, you push this 7 inside this. When you push 7 inside this, you have 3, 4, 7, and then you print the contents of it, which is this. Now again, you would want to make sure that you pop this 7 out, because if you do not pop this 7 out, that will be reflected in all the other paths. So when you pop this, you will get back from here to here. And now when this is over, you come over here. Now again, this was the point where you had pushed this 4. So now again, it is your responsibility to pop this 4. When you pop this 4, then you go back there and then you tread on to the other paths. That is the reason it is very important to pop whatever you had pushed, because I told you, you are at a node, you push that node and you travel. But once this recursion is over, please pop this node, because along other paths, this node will just not be there. Is it now clear to everyone why that pop is there? Okay, cool. Yeah, so any thoughts about the time complexity of this program? Okay, most of you are saying order n. So let me tell you, it is not order n, it is different. It's an interesting question. Lot of people, even good programmers, make this mistake. When I ask this question, that what is the complexity of this program? So if you're making this mistake, no worries. Let's learn through it. Let's say you have a tree which looks like that. Okay, how many root to leaf paths will be printed for this tree? Only one. And what is that path? That path is 1, 2, 3, 4, 5. Let me write it 1, 2, 3, 4, 5. Okay. Do you understand it here that each integer is printed only once? 1 is printed once, 2 is printed once, 3 is printed once, 4 is printed once, 5 is printed once. Okay. Let's take some other example. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. How many root to leaf paths will be printed here? 8. Okay. And what is the first path going to be? 1, 2, 4, 8. Second path will be 1, 2, 4, 9. 1, 2, 5, 10. 1, 2, 5, 11. And then you have 1, 3, 6, 12, 1, 3, 6, 13. I hope I have not missed something. 1, 3, 7, 14. You can check that. 1, 3, 7, 15. Okay, here also can I say that each integer is printed only once? The answer is no. How many times this 1 got printed? 8 times. 1, 2, 3, 4, 5, 6, 7, 8. How many times this 2 got printed? How many times 3 got printed? Okay. 2 got printed for 4 times. 3 also got printed for 4 times. You know, there is a very strong reason why. Because how many paths cross this 2? 1, 2, 3, and 4. Similarly, there are 4 paths that cross this 3. So you can see that 2 has got printed 4 times, 3 has got printed 4 times. Now, how many times this 4 has got printed? 2 times, because there are 2 paths that cross this 4. So 2 times this 4, and this 5 also has got printed 2 times, because the first path is this, second path is that. Similarly, this 6 also 2 times, and this 7 also 2 times. Okay, how many times each of these leaves have got printed? Each of these leaves have got printed only one time each. So 1 time this, 1, 1, 1, 1. Okay, now let's be realistic. What is the total number of prints at first level? Total number of prints at first level, 8, correct? What is the total number of prints at second level? 4 plus 4, again 8. 4 times this, 4 times that. Total number of prints at this level, 2 plus 2 plus 2 plus 2, again 8. And total number of prints at this level, 1 plus 1 plus 1 plus 1, again 8. Do you see it? Yes or no? Right? So I can say that at each level, the number of prints which is happening is 8 only. This is a point which is worth noting. Correct? Okay. Now what I can say is that if the tree is perfectly balanced and there are n nodes, then how many levels will be there? Or what will be the height? How many levels will be there if the tree is perfectly balanced? It will be log of n base 2. Okay. It will be log of n base 2. And now think and say, if there are n nodes, then roughly how many nodes will be there at the last level? There are n nodes, roughly how many nodes will be there at the last level? Roughly n nodes will be there at the last level. And you know, it is something which is very, very easy to understand. You know, last level has maximum number of nodes in case of a perfect tree like that, because you can see here the total number of nodes are roughly 15 nodes, and out of 15, 8 nodes are there at the last level. Okay, you can cross check that. It can be mathematically proven as well. So I can say roughly n by 2 nodes, which is half of the nodes will be there at the last level only. Okay, half of the nodes will be there at last level. So I can say that each of these nodes will get printed 1, 1, 1 time. Okay, now each of these nodes will get printed 1, 1, 1 time. Each of, sorry, 2, 2, 2 times. Each of these nodes will get printed 4, 4, 4 times. Each of these nodes will get printed 8, 8 times. So I can say that if there are log n levels, right, and if there are n by 2 root to leaf paths, because there are those many leaves only, then total complexity will be n by 2 into log n. This 2 can be ignored, so it will roughly be n log n. Now, what is this n by 2? This n by 2 is simply equal to number of leaves, which also symbolizes number of root to leaf paths. So it means that there will be n by 2 paths which will contain one in it. Similarly, there will be n by 4 paths which will contain this, and n by 4 paths which will contain this. N by 4 plus n by 4, again n by 2. N by 8 paths which will contain this, n by 8 paths which will contain this, n by 8 paths which will contain this, n by 8 paths which will contain this. Again, n by 8 plus n by 8 plus n by 8 plus n by 8 will be n by 2. So I can say that there are almost log n levels, and at each level, the number of prints that is happening, that is almost n by 2, which is n. So total data which will be printed will be almost n log n, where n is the number of nodes. Does it kind of make sense? Yes or no? Yeah. So a lot of people who say that the time complexity is going to be order n, that is not right, because when the tree is balanced like that, then a particular node will be printed again and again. Okay. And this is quite contrary to the case of a skewed tree. In case of skewed tree, only a node will be printed only once. Do you understand the role that structure of the tree plays in case of the time complexity? Yes or no? Yeah. Okay. Any confusions? Anything that you want me to say again? Some of you already have some sort of confusions, but you will have to tell me like what exactly is confusing. What is n by 2? What is n by 2? How many leaf nodes are present over here? You have a perfect tree, right? If there are n nodes in a perfect tree, then maximum nodes are present at the leaf level only, and that count is n by 2. So what I'm saying is that there will be n by 2 root to leaf paths. As simple as that. Okay. Now, when you look at these n by 2 root to leaf paths, I can say 1, which is your root, will be present in all the n by 2 paths. So it means this will be printed n by 2 times. When you look at this 2 will be printed n by 4 times. This 3 will be printed n by 4 times. And what is n by 4 plus n by 4? It is again n by 2. So total number of prints for the nodes at this level is n by 2 again. Now, when you look at this 4, it will be printed n by 8 times here and here. This 5 will also be printed n by 8 times. This 6 will also be printed n by 8 times, and 7 will also be printed n by 8 times. So if you compute the total number of prints for the nodes at this level, it will be n by 8 plus n by 8 plus n by 8 plus n by 8, which again is overall n by 2. So do you see that total prints for all the nodes of a level when summed up is n by 2, where n by 2 is the number of root to leaf paths. Is that now making sense to others? Those of you who are surprised still about what is n by 2. Yeah, okay, think a bit more about it. I mean, it can even be your food for thought. Should be clear. Nothing too special about it. Okay, let's move on. Okay, so now we will talk about another really, really important property of tree, and that property is called as diameter. So you have been given a binary tree and you need to find its diameter. How many of you heard about diameter of a tree? Can you define it for me? What is diameter of a tree? You must have heard about diameter of a circle. So I think everyone heard about diameter of a circle, right? This is a circle. It has a center. What is diameter of a circle? Define the diameter of a circle for me. Maximum number of nodes at a particular level. No, that's not the right definition. Just define the diameter of circle. You are saying diameter of the circle is 2r, okay. Longest chord. So what is chord? Can I say diameter of a circle is, if I call this point 1 and call this point 2, this is the longest distance between any 2 points. Can I define it in a layman language like that? Yes or no? Yeah, yes, no. Can I define the diameter of a circle as longest distance between any 2 points? Correct. That is how the diameter of binary tree is also defined. It is longest distance between any 2 nodes. Got it? You guys can remember it now? Longest distance between any 2 nodes. Okay. Now, yesterday, I had told you one very important thing. If there is a tree and you select any pair of nodes, N1, N2, then how many paths are there in between N1 to N2? One and only one path, correct? Via sequence of edges. So let's take a quick example. I'll want you to find diameter of a particular tree. Let's say you have 1, 2, 4, 6, 4. Yeah, can you tell me the diameter of this tree? Okay. Some of you are saying that the diameter is 3. Some of you are saying that it is 7. Okay, so tell me, what are the 2 nodes which you are considering? Which 2 nodes have the largest distance between them? 7 and 4. Okay, let's take this 7 and this 4. Can you tell me the distance between this 7 and this 4? By distance, I mean how many nodes are lying along that path. How many nodes are lying along the path from the 2 underlined nodes? So if you have to go from this 7 to that 4, you will go like this, like that, and like that. So this is the path. And along this path, the number of nodes are 1, 2, 3, 4. But if instead of taking this and this, if you take this and this, now can you tell me how long the path is from here to here? So you have to go like this, that, this, that, this, that. So the number of nodes along this path, as you can see, are 1, 2, 3, 4, 5, 6, 7. And this looks like the most promising, the longest path. So the diameter over here is 7. Is it now clear to everyone what is diameter? Yes or no? Yeah. Any confusions? Yes, no? Okay, cool. See, next question that I would want to ask you is, some people also say that the 2 nodes between which the distance is maximum, those 2 nodes have to be leaf nodes. Certain people conclude that. Is that right? Is that right to say that the 2 nodes having longest distance between them will be leaf nodes only? Many of you are saying yes. Okay. Okay, by the way, one of you asked it's number of edges and not the nodes. Again, I'll tell you it's just a convention. Certain people count number of edges, certain people count number of nodes. I am counting number of nodes. So for me, the diameter is number of nodes that determines the length of the path. It's not the number of edges. Okay. Cool. So my current question was, is it necessary that the 2 nodes having maximum distance will be leaf nodes? So most of you are saying yes, and that is not true, because if I, let's say, tell me the 2 nodes between which the distance is maximum. One and 5, right? If you consider 1 and 5, the distance between them is this, which is of 1, 2, 3, 4 units, right? And is one a leaf node? One is not a leaf node, correct? So never ever say that diameter is longest distance between two leaves. Certain people say it is longest distance between two leaves. No, it is longest distance between two nodes, and those two nodes can be anything. An important point it is. Is that making sense to everyone? Now tell me one more thing. Certain people also say that, hey, the diameter of a tree, which is the longest path, will always pass through the root. Like in this case, this is that path which gives your diameter, and it is passing through the root. So sometimes people say it will always pass through the root. Is it correct? Yes or no? The answer is, again, it is not correct. So we can have a quick example. Let's say you have got what is the longest path over here? Which two nodes will you pick? The two nodes that you will pick over here will be 12 and 7. If you pick 12 and 7, then this is the path that you will have. And this path clearly does not pass through your root, correct? So this is again an important thing to be kept in mind. Okay, cool. Makes sense to everyone? Now, tell me, how do I solve this problem? So the way to go is recursion, but how exactly can we use recursion? Think of that. Okay, one of you is saying it will be max of height of right left plus max of height of right right. When you are doing max of something, then there should be two things inside it, right? Okay, Satish is saying 1 plus max of root left, root right. And what do you mean by max of root left comma root right? Think a bit more about that expression. One plus max of, see, when you are doing 1 plus, you are always taking into account the root. But I told you that you don't know that which nodes your diameter will be passing through. Listen to it. It is a very important point. You don't know which node your diameter will be passing through. In case of height, you knew it, that height will always pass through the root. But in case of diameter, it is not necessary that it will pass through the root. It can pass through any other combination of nodes. That's not known. So let's think of it. It's a good problem. It's a well-known but a good problem. If you conceptually understand it, you will be able to solve many questions on trees on your own. So let's conceptually get it. See guys, can I say that diameter will be a path which will take turn around some node? It will take turn around some node n. When I say turn around, like here it is taking turn around this node, and in this example it was taking turn around this node. Now what is that node where turn around is being taken? That I don't know, but there will be a node for sure where a turn around would be taken. Yeah, in cases like this, you can argue and say that there is no turnaround, but I would say, hey, I can consider that, hey, this is the point where turnaround is there. It's just that the other part is empty. Okay, is it making sense to all? Yes or no? Right. Okay. Now, if I have been, let's say, given a tree, if I've been given a binary tree, now what I'll do is, for each node, I'll assume it as my turnaround point. So assume it as my turnaround point. If this is supposed to be my turnaround point, then what is the longest diameter? Then what is the diameter that I can have? Then what is the longest path that I can have? So in other words, can I figure out the longest path that passes through it by taking a turnaround from here? So the answer to that is very simple. If there is a node, let's call it N, and if it has a left subtree, call it LST, and has a right subtree, let's call it RST, then the longest path that passes through it by taking a turnaround will simply be equals to 1 plus the height of left subtree plus the height of right subtree. That is the longest path that passes through it and takes a turnaround. Does it make sense that how it is 1 plus height of left subtree plus height of right subtree? Yes or no? Right? Like here in this case, what is the height of your left subtree? The height of your left subtree is 1, 2, 3, 4. The height of your right subtree is 1, 2, 3. And 4 plus 3 plus 1 is 8. And that is the longest path which passes through it, taking a turnaround. Now, if you compute this thing for all the nodes, then the maximum value of this, which you get for some node, that will be your diameter. Like if you are computing this expression for this node, this node, this node, this node, this node, all the nodes, then whichever node gave you maximum value of this, that maximum value will be your diameter. And why I am calculating it for all the nodes? Because I don't know what should be my ideal turnaround point. Is it now making sense to all that how this idea is true? Yes or no? Correct. So this is exactly what we'll be doing. So just to get more comfortable, I'll draw one more tree. Let's say we have 1, 2, 3, 5, 7, 6, 11, 4. And let's say here we have 8, 9, 10, 7. Can somebody tell me the diameter of this tree? 4 to 7. And what is the length of that? So I believe you guys are talking about the path that goes like that. Are you talking about this path that I just showed? Yes or no? Yeah, so that is the answer. Think of it in this way. If you compute this expression for all the nodes, what are the values that you are going to get? Can you tell me the value of this expression for this node? If this is my turnaround point, then what will be the value of 1 plus height of left and plus height of right? So for this node, what is the height of left subtree? The height of left subtree is 1, 2, 3, 4, 5. And the height of right subtree is 1. So 5 plus 1 plus 1 is going to be 7, right? Now let us compute this expression for this node. What will be the value of this expression for node 3? For 3, the height of left subtree is 0. The height of right subtree is 0. So 0 plus 1 is going to be 1. Similarly, if you compute it for this 2, you have already computed it for 2. That turns out to be how much? I believe 9. The height of left is 1, 2, 3, 4. The height of right is also 4. 4 plus 1. So similarly, if you list down this particular value for all the nodes, whatsoever will be your maximum, that will be your answer. So this is the idea. Now, how many of you can code this idea? Okay, so you can very easily code this idea if you remember how I had written the code for finding height of a tree. Do you guys remember the code for finding height of a tree? How was it written? Height of the tree rooted at root is equals to 1 plus maximum of height of the tree rooted at root left, comma height of the tree rooted at root right. Okay, so I'm going to write something on the board, guys. Imagine there is a big tree. Okay, like that. This is some tree. it has LST, and it has RST. So I'll illustrate you that we have talked so much about it, and now whatever we will be writing, it will be written in terms of left subtree and right subtree again. So if I have to find the diameter of the tree rooted at this root, then I can say my first option is that the path which corresponds to the maximum height passes through this itself and takes a turn about it. So that will be equals to 1 plus the height of root left, which is height of this subtree, plus the height of root right. But this is just one possible option, because in this case also, this was not the diameter. So what are the other two options, or what are the other options? The other options are that my diameter could either be contained entirely in my left subtree, or it could be contained entirely in my right subtree. So my diameter could either be contained entirely in left part or entirely in right part. So if dia of root tells me the diameter of this, then dia of root left will tell me the diameter of this recursively. Similarly, dia of root right will tell me the diameter of this. So the second option that I have is dia of root left. And the third and final option that I have is dia of root right. And whatsoever is the maximum of these three values, that will be the diameter of root. So just summarizing it again, if you have to find diameter of a tree rooted at root, then the first option is that this root itself is the turnaround point for which this expression is written. And the second option is that the diameter is entirely contained in this. And the third option is that the diameter is entirely contained in that. And whatsoever is the maximum of these three things, that will be the diameter, overall diameter. Is this expression making sense to everyone? Just type in yes or no. Yeah. So that's all about it. Now you can have your job done. So now just tell me one thing. Can you write this height function? We have already written this height function. You can refer to it. So there can be a height function which takes the root of the subtree whose height you want to compute. So you can just call it. Okay. So you can, so if you pass to this, height function, this node, then it will return you the height of this tree. If you pass to this height function, this node, then it will return you the height of this tree. So whenever you want to compute height of a subtree, whether it is left subtree or right subtree of a node, you just have to consult this person or this method, right? And then you can keep on recursively calling this method again and again. So if I have to write a code for this that aligns with this idea, I'll say there is a method that returns me diameter, and it takes the root of the tree, the original tree. And then what it does is it returns me the maximum of three things. So what are those three things? The first thing is 1 plus this entire thing. I'm just copy pasting it over here. The second option is make a recursive call for your left subtree. And the final option is make this recursive call for the right subtree. That's it. So this is your recurrence relation kind of thing, but there has to be one termination condition also. Can you think and tell me what will be your termination condition? So whenever from a root, you are making calls to your left and right, that means you are coming down. You're coming down and down and down. So eventually, let's say if you were here, you will make a call to null also. Can you tell me what will be the diameter of this empty tree? What's the diameter of an empty tree? The diameter of an empty tree is 0. Does it mean that I can add a termination condition saying that, hey, if my root is ever null, then just return 0. Otherwise, do this chunk of task. And what is this? First, compute the height of the left subtree by making this call. Then compute the height of right subtree by making this call. Figure out this value. And then try to find the diameter in left subtree and then the diameter in right subtree, and keep doing this thing on and on and on. Make sense? I mean, if you get the code. Okay, great. Can you talk about the time complexity here? If there are n nodes, how many operations we are doing? Okay, 2 people are saying n square. Tell me one thing, how many of you feel that it is definitely not order n? You might not be sure whether it is n square or n log n, but do you feel it is definitely not order n? Okay, now tell me, why do you feel it is definitely not order n? If you are able to give me that answer, I'll be pleased. You know, it is definitely not order n because at each node, you are making call to this height method. So when you are here, you call height method. When you are here, you call height method. When you are here, you call height method. And call to height method, is it order one? Does height method work in order one time? The answer is no. The height method works in order n time, where n denotes number of nodes of the subtree whose height you are trying to compute. So in the worst case, what will happen is, if you have a skewed tree as your input, then you will call your diameter function for this node. Keep looking. When you call your diameter function for this node, you will first try to find the height of this much part. When you try to find the height of this much part, if these are n minus 1 nodes, this thing will take n minus 1 time, right? Now, when you recursively call diameter function for root right, and when you are here, you will now try to compute the height of this much part, and it will take you n minus 2 time. Then when you are here, you will try to compute the height of this much part. It will take you n minus 3 times. So it will go till 1. So the sum from 1 to n minus 1, it will roughly be n square. And why is it happening is because you are first asking this to give you this much height, and then you are asking it to give you this much of height, and then that much. So a particular node is getting touched again and again and again. Is it making sense to everyone that how it will shoot to order n square? Just type in yes or no. Yeah, quite important to understand. Okay, cool. So although it is taking order n square time, but it is a right approach, it will give us correct output and we'll be happy about it. But now I want you guys to optimize it. Can we optimize it somehow? Think of that. Okay. Tell me one thing again. Do you remember that I had drawn for you a recursion tree diagram of how the height is computed? Recursion tree diagram of height. How many of you remember this? I had drawn it just 30-40 minutes ago. So those of you who are really thinking deeply, you will understand that whatever we are doing over here, according to this particular thing, is a very stupid thing to do. Why it is a stupid thing to do? Because think of it in this manner. If this is a tree and you ordered height for this much part, if you ordered height of this much part, can you think how would it internally have been computed? It would have been computed by first finding the height of this much and then finding the height of this much. And then again, for this to be computed, it would have computed the height of this much and then the height of that much. So what is happening is, in one call to the height only, the height of all the subtrees are being computed internally. You get overall height after you have computed height of all the subtrees starting from bottom to top. Is that somehow making sense? Yes or no? Correct? So if you are ordering height again and again, like once you were here, you ordered height for this and that, and once you are here, you ordered height for again this and that, then this is not a great thing to do. So what you can do is you can modify your height method and you can get your job done. Now, what I mean by modifying your height method, so let's talk about it. Let's say you have something like this. Okay. Now, you know how it works. So if you call height function on 1, it will call height function on 2, and then it will call height function on 6. Now again, from 2, you will call height function on 4, height function on 3. From here, you will call height function on null, height function on 5. And from here again, height function on null, height function on null. Now you see what happens. So from null, you anyways return 0. Again, from here, you anyways return 0. You anyways return 0. Can I say that whenever you are at a node, you have your left height also, and you have your right height also. Like once you return from here, then at this node, you have your left height also, and you have your right height also. Similarly, when this returns and this returns, you have your left height also, and you have your right height also. So whenever a control comes back to a node from bottom to top, you have your left height as well as right height. And if you have your left height and right height at each of the nodes, then you can very easily compute this thing, which is 1 plus LH plus RH. And now what you can do is you can have a global variable, which is answer. You can initialize it to 0, and you can keep on maximizing it. So at each node, you can say answer is equals to max of answer, comma, 1 plus LH plus RH. Is it making sense what I just said? Yes or no? Yeah. So all that we are doing is we have a global variable answer, which is initially 0. And now we know the way our height function works is whenever control returns back to a node, we know its left height and we know its right height, and we know it for all the nodes, right? So what I'll do is I'll create this expression, and if this expression is greater than answer, I'll update my answer. This answer is a global variable, or you can pass it by reference if you want. Job will be done. Right? How many of you can code this logic? Just type in yes or no. So we go from leaf to root. I mean, no need to worry about that. You just have this recursive method. You just plug this thing inside that recursive method and job will be done. So I'll write it for you. So I'll write height function again. Let's say I have a get height, and it takes the root of the subtree whose height is to be computed, and you're passing answer variable by reference. You want, you can keep it global. You know, I would advise you against global variables, because on certain platforms, global variables, they behave very, very abruptly. Okay, so let's keep taking a look at this code. This code is not responsible for giving you diameter. This code is responsible only to compute height of the overall tree. Okay, so what did we write here? If our root is null, return 0. Otherwise, what was the first step? Get the height of left. Get the height of root left. Okay, store it in some left height. Similarly, get the height of root right. Okay, now, you know, this get height method is being recursively called. So it will be called for this node, this node, this node. It will be called for all the nodes. Now, if the control comes back to this node, you will have left height also, you will have right height also. So if you have left height and you have right height, so you can create this expression. And if this expression is greater than the current value of answer, you can update your answer. So you can just put a line over here, answer equals to max of answer, comma, 1 plus LH plus RH. And then return the actual height, which is 1 plus max of LH, comma, RH. So, you know, this is the only new line which has gotten introduced over here. Everything else is still the same. You are still at a node, you are getting LH, RH, and you are returning the height by using this formula to your parent. So while the height is getting computed, you very silently put this line and compute diameter also. And how you do that? You know the left height, right height for all the nodes. You know 1 plus LH plus RH, and you use that to maximize a variable answer. Is it making sense to everyone that how and why this code is logically correct? Yes, no? Yeah. Okay. And what will be the time complexity of this code? Will it still be order n square? The answer is no. It will be order n, because what was the complexity of height method? The complexity of height method was order n, and you are doing nothing to change it. You have just added one new line, which is doing some constant number of operations at each node. So it will continue to be order n. Does that make sense to everyone? Okay, so when you go back, please make sure you code all the ideas that we have discussed today. Even if we have discussed some suboptimal ideas, then it will be worth coding them. Okay, let's take one final question for the day. So there is a very well-known category of binary tree, and that is called as, it's called as height balanced binary tree. So what is the height balanced binary tree? Please explain the time complexity of this again. Did you understand the time complexity of height, just the height function? It was order n, right? So in the current code, what are you doing? In the current code, at each node, you are just finding 1 plus LH plus RH. You're adding 3 integers. Adding 3 integers is order 1. So it will continue to be order n, right? At each node, you are doing constant work. It's not like at each node you are calling some other function, which again is going to take order n, which was the case in get diameter method, right? Do you get that? So it will continue to be order of n. Yeah. Anyone who knows what is the meaning of height balanced tree can define it for me? So height balanced tree is that where for every node, the height of left subtree and right subtree must not differ by more than 1 unit. This is the formal definition of height balanced tree. So height balanced tree is that in which for every node, the height of left subtree and right subtree must not differ by more than 1 unit. Does the definition make sense? Yes or no? Okay. You know, I can formally write it in this manner. For every node, what should happen is that height of left subtree, which is an integer, minus height of right subtree. And I have to take its absolute value because I don't know which one is larger, which one is smaller, because all that I need to ensure is that their difference, their absolute difference is smaller than equals to 1. That's what we want. So let's take a quick example. What are your thoughts on this? Is this tree a height balanced tree? Yes or no? Right? Okay. So tell me one thing. Let's say if you take this node, what is the height of left subtree? 2. And what is the height of right subtree? 2. What is 2 minus 2? It is 0. And 0 is smaller than equals to 1. It looks like it is a very simple problem, isn't it? Can I just find the height of left subtree by invoking height method for root left and then find the height of right subtree? So if I call this as h1 and I call the other height as h2, all that I can check for is this much. So I'll do this check only for the root. Will that be sufficient? The answer is no, it will not be sufficient because the question clearly says for every node, this condition has to be true. Okay, for every node, this condition has to be true. So if instead you have something like this, Okay, if you perform this check only for the root, will this check be true or false? Only for the root, tell me. The check will be true. Why? Because the left height is 3 and the right height is also 3. But will you say this is a height balanced tree? No. What is the culprit node over here? Which node is not abiding by the rule? Yeah, this 2 is not abiding by the rule, because for this 2, the left height is 2 and the right height is 0, and 2 minus 0 is not smaller than equals to 1. Correct? So what you have to do is you have to perform this check for all the nodes. So you can solve this question exactly like diameter question. So at each node, you can first find left height, then you can find right height, and then you can check for the difference. Do you understand? Do you at least get a hint of how you can code this problem? Yes or no? But you know, you can play much smarter, because if you take the approach that was our first approach of diameter, it'll take you order n square, because from each node, you'll call height for its left child. Then again, you'll call get height method again and again. Rather, what you can do is in the height method itself, let's say you have invoked height call for this. Now, whenever you are at a node, you would know what is the left height and you would know what is the right height. Okay, you would know left and right height. So if you realize that this thing ever becomes greater than 1, then you can turn your answer equals to false. And this answer can be a Boolean variable, which you can again keep global, or you can pass it by reference. Okay, so you let your get height method remain as it is. The only trick that you play is whenever left height and right height have been returned for a particular node, just check for their difference. If their difference exceeds 1, then you turn your answer variable to false. That's it. Does it make sense? Yes or no? How many of you got that? Right? How node 2 is the culprit node? For this node, what is the left height? What is the left height? 2 units. What is the right height? 0 units. What is 2 minus 0? It is 2, which is greater than 1, right? Clear? Okay, cool. So how many of you can code this problem now? Do you feel confident enough to code it? It's an easy question, was recently asked in an Amazon interview. Do give it a try. So that's it for today, guys. You can now go back and we'll meet again tomorrow. Solve the questions. They are already there out on your dashboard. Yeah. Okay, so bye. Have a good day. Tomorrow we will continue more with trees only. Okay.